And good afternoon from windy and wet Stellenbosch. I'm Lorraine Kuhn. I teach at Huguenot High School in Wellington. And my friend here next to me.
Thank you, Lorraine. And I'm Colin Oppold, and I'm from New Orleans Secondary in Paul. And I hope all my learners are logged on and in. And but to all of those out there, welcome, grade 11, to your first session of telematics. And we really hope that you're going to enjoy all of these lessons, but especially today's lesson, Lorraine. We have somehow a surprise for them here today.
I think they can see it, and I hope you're not too hungry, because we're hungry too, and we're not we can't really eat while we teach. Today we have a lesson on hypothesis testing and the scientific method, something with which so many learners battle. So if you follow us step by step as we work through this lesson, we hope that at the end you will be much more confident in answering questions on the scientific method and hypothesis testing. You also have a handout, most of you we hope, on this work for grade 11, and the contents, there are questions with answers on the topic, as well as next time's topic, when we will talk about the human impact on the environment. But Colin, let's get started without any further ado.
Yeah, we've been quite busy today in the kitchen.
Well, you've been busy baking.
Exactly. But you see, with hypothesis testing, it's always a problem when we start planning a scientific investigation. Because there are certain things that you need to keep in mind when you do it. So you need to get things in order, and that's called planning. And this is also one of the questions that grade 12 learners and grade 11 learners get in an exam. And then they talk about doing the investigation instead of what are those steps that they follow when they plan to do a scientific investigation.
In other words, step one is the planning, even before anything else. Yes, let's continue.
Let's look at the slide and we say, what are those things that we need to keep in account? So those factors that you need to keep in account before we conduct an investigation. So Lorraine, we need to think, who or what are we going to test?
What is our investigation all about? Because that will determine what we need to get together, what we need to get permission for, what materials, apparatus, venue we need to get. So yes, we need to go and sit down and have a good think about what we're going to test. And then, of course, as you've seen on the slide, when you do that, you think of your sample group, whether it's humans or whether it's muffins, as we have here today. But yes.
Yeah, and I think when you think of how big or how large is the group that you're going to work with, is it doable? Are you going to plan, if you do something where you have a questionnaire and you have to do research within your community, you're going to ask, am I going to take one specific area? Am I going to take the whole town? And then you need to understand, how are you going to get to every person within that town? So if you think of your sample group, that's very important. And then also the measure, how are you going to test it? Am I going to use a questionnaire, as I've already said? Am I going to do some research? Am I going to put out certain things to observe certain changes? You need to really think about, how am I going to do it? Where are you going to do it? Am I going to do it in a place where people are going to walk and maybe ruin whatever I'm trying to put out there? Or do I have to put it in a place where there's sunlight? Do I need to put it in a place where there's wind or no wind, etc.? So a lot of things that you need to keep in account when you do that.
And just before we get to the planning of the investigation, should you get a question on write a few steps for planning, and we're going to continue with them. Just a reminder, you will be given a scenario, in other words, what you need to test. So your planning steps need to apply to that specific question. You can't have generalizations as we're doing here now. For instance, we said who are you going to test? The question will already tell you. So let's continue, because that really will have bearing on how you do it.
Right, and here we get to the section where learners always they struggle with identifying the variables. But let's see, if you're going to have certain things that you need to keep the same, those are the fixed variables. And if we can just have a look in front of us, we have here cupcake holders because we're going to do the muffins. If you look at it, there are different colors, but they are all, if we look at all of those, you can see that they are all the same size, they are the same make. It's just the outside color that differs.
Yeah, and that's even the same type of foil cupcake holder. For instance, so when we said we're going to bake muffins, we couldn't very well just go and look in the cupboard and see and get all the cupcake holders together. We needed to make sure that they were all the same. It's part of your planning. If you don't have them all the same, then you need to go out and buy them.
Right. Then, and when you get to planning the investigation, we'll get to this later on.
Yeah,
but you need to understand what are we going to manipulate or change, and that means what is my independent variable and what am I going to measure? How am I going to measure? Am I just going to make an observation? That means how am I going to look at the changes that take place within the dependent variable?
And if your head is spinning now, that's exactly why we're going to do it. All these terms that we've used, all these aspects, we're now going to start with step by step. So concentrate. Don't try to write down, just concentrate on what we're doing.
And if you look on the slide and you see a spelling error, it's a typing error, okay? We touched on to those already. Those are the factors that you keep the same. So whatever we're going to, let's start looking at the muffins. We already said we're taking and we're keeping our muffin cupcake holders the same. It's the same size, it's the same type, it's the same material, and it's just the outside, the different colors. And why did we use the different colors? Because we are going to change our procedure into an investigation.
No, it's and that's just to make sure that we know which cupcake is which. And Colin, I saw the photos which our learners will see soon. You had your people at school make the cupcakes and mix the cupcakes this morning. And I remember from last time you made sure that they had the same bowls and the same way of mixing, etc.
Yes, there you can see.
Yes.
This is now last year's photo that I couldn't take a lot of photos because we had to make it today. We can't use old stuff here. And there you can see the bowls. All bowls are the same size and the same type of wooden spoons, the same amount of muffin powder, the mixture that we have there. We have the same batch of eggs that we used. We had the same amount of water, even the measuring cups that the water was in was the same. So those are all the factors, the variables that we kept constant, and those are the constant variables.
And why do we need to have fixed variables?
You know, that's very important. If we have different eggs from different, say, batches of eggs that we bought at different stores, we don't know whether those eggs came out of from different places, they were fed differently, they might have an effect on the results of our investigation, and that is why we need to keep everything as valid as we can. So
in
to
other words,
increase
it's
the validity of our investigation, we keep all those things that we can keep constant or the same.
Because we only test one thing at a time, and we can't allow anything else to influence our results. So as Colin has said, it is to make sure that our results are valid. It's for improved validity. Good.
Okay, this one was taken this morning. It's the same amount of muffin powder, which means I had a scale and I had to measure 250 grams of this muffin powder. Even the time, I had those there, you can see 4 learners at a time, and they all do the same thing at the same rate, which means that when they started mixing, I made sure that they mixed at the same rate and nobody was faster or slower than the others. We had a time, we kept the time, 30 seconds for the first and 2 minutes with a spoon. So there we used a measuring cup. This was also last. If you see it's chocolate, you know the batter is different, but it doesn't matter. We used the same measuring cup. So we try to put in each mold the same amount of batter. And this is why it is so important to keep those constant, so that it increases the validity of our investigation.
In other words, we make sure that the only factor that affects our investigation is the one that we test. And this now is important for our next slide. How do we identify the different variables?
Let's look at our independent variable, Lorraine.
Yeah, that is what we test, what we change, what we manipulate, what you decide on, what you have control over. For our cupcakes, for instance, we're going to test the influence of various ingredients on the height of the cupcake. So, it's jumping now.
I actually wanted to go to the slide.
Yeah, the ingredients. Just go back to the previous one. Thank you. The independent variable.
Where am
Previous
I?
one.
There we
Yes,
are.
there we are. Sorry about that. In other words, we decide which factor we're going to test. So that is your independent variable. And then we go to the dependent variable.
And there we have the one. And your dependent variable is the one that you observe, the change that is taking place. Either you can measure it, or you can observe, see, for instance, whether there's growth. So something that you can see, it's the results that you obtain from doing the investigation. So it's very...
It's the results that you're waiting for.
Yes.
You are waiting to see what's going to happen. What is going to happen is your dependent variable.
Right. And so when we have a recipe, so we decided we're going to do the muffin, so we have a procedure. And when we follow a procedure, we just simply follow the recipe. And the recipe is prescribed onto the packet. There you have, we use the Easy Mix. We're not trying to advertise this. But then we started, what are we going to do? We have to test something, and we said, what is our aim of this investigation? And the aim of investigation, it always starts with to determine, or to measure, but you want to do something. What is it your aim is? So we want to determine the average heights of 6 Easy Mix muffins. So in front of us we have 4 because of our time restraints, but we have made 6 of each.
Yeah, and it's for each independent variable that we're going to test. So actually in the end it's to determine the effect of adding an ingredient to the mix. Now if we look at this list, it's our recipe, and this is the list of materials and apparatus that we're going to use.
Yes, and I've highlighted the ones there. Those are the ingredients: the eggs, the 1/4 cup of cooking oil, the 100 milliliters of water, the amount of Easy Mix powder that we've used. And we said, if we want to change this procedure, we must look at our ingredients that we can change. I mean, the mixing bowls, the measuring spoons, they remain the same. But we can say, what is going to happen to the height of our muffin if we add an extra egg, for instance? Or if we add 1/2 cup instead of a 1/4 cup of cooking oil, we take twice the amount. What's going to happen to the height of our muffin? Instead of 100 milliliters of water, what's going to happen if we add another 100 and we use 200 milliliters of water? You see? So the factor that you manipulate or that you're going to change, that's your independent variable.
Can you see what we're working here towards? Every time we have one factor that we're testing. When we say what will happen to the height of the cake when we add 1 egg to our mixture, the 1 egg is the factor that we change, our independent variable. Our question asks what will happen to the height of the muffin. So that is what we're going to wait for. That will be our dependent variable. And that is one investigation. Investigation number 2 is the water, the extra water. Because it's so important, Colin, and we will talk about it again, that we only test one factor at a time.
Yeah, and as we have this wide screen in front of us, there you can see over there, we have the control, And the control is the procedure that we follow. Here we can see is another set of 4 muffins. That was when we added an extra egg. Here in front of me, I have the water, extra water added to it. And if we get to it, here I also added baking powder. So if we have time to get to it, but I know at the end of this, you will get what we're actually trying to say. So let's look at the control.
Let's get started.
Following the procedure, we use there, you can see all the equipment that we've used, and that is what the batter looked like. So we didn't change anything. So let's go and let's measure the height of it. And this is another thing. You see there we have prepared in front of us, we have a table. So you need to decide how am I going to record my results. And the one that Lorraine has in front of her is a little bit different because we are doing more than one investigation here to show you how you can change one simple recipe and you can change one ingredient and you have more than one investigation. So,
Right, let's, from that table, we're going to look at the table that we have on the board here and where we're going to work. And this is one of your planning steps, is to prepare some way of recording your results. So, Carla, let's start with the control. That was our standard recipe.
may I have 2 of those,
Yes,
please?
you're getting 2 of those, and I have 2 of those.
It's a pity we have to cut it up and we can't even eat it, eh?
And if you're hungry, we're hungry too,
Okay.
but we'll...
So we
I know.
remove the cupcake holder here. And first of all, to measure this, how are we going to measure it? And unfortunately now, we don't have the one that I wanted to show you the one and the 2 halves, but we cut where we see the highest part of the muffin. And you take a ruler, and even the 2 of us have the same, we have the
they're
same
different colours.
makes of ruler here.
But they're the same type.
Yes.
Well, I
Yeah.
can't say the name, but they're the same.
Right.
Let's have a look how we measure from the 0 line to where it is the highest, and I must not make the parallax mistake.
Okay.
So if I do it, this muffin half is 41 millimeters, 4,1 centimeters, and I write there 4,1.
That's strange. Mine is 4,9.
Sure. How did that happen? And I cut through the next muffin, measure it,
This one is also 4,8.
and this one is also 4,1. I was cheated.
Really?
You say 4,9 and 4,8.
Yeah.
Right. And now we need to get an average.
And if you really want to work accurately, you can use this. But I mean, you can easily see there is 4.1, 4.1, and we have
4.8,
4.8 plus
4.9.
4.9, and we divided. No, sorry, I didn't put the 4.
By
4.1. 4.1. 4.8 plus 4.9 divided by 4. And my phone
What
is
is-
not working.
the phone or the operator?
I think it's the operator.
It is if we round off, it's 4,5 centimeters, the average.
Yeah, you're much quicker than what I am here.
Why do we need to get an average? Can you see the difference? So by getting 4 muffins instead of just 1, 4 muffin halves that we measured, we can improve the reliability
Very
of our
important word.
results.
Very
Yes.
important word. You remember right at the beginning we asked, are you going to decide on your sample size? How many of a kind are we going to use? If we only had 1 muffin here, how reliable would this investigation have been? But now we took 4 muffins, determined the average of the 4. That means that we have increased the reliability because we have taken more than 1. Very important, Lorraine.
Right, now we have our control. That is the standard recipe without any change, and we use it to compare the results of our investigation. We need to benchmark something to compare with to see if there really was a change. So that is the purpose of the control, is to compare our results against. So let's take the muffin now, Colin, where we added 1 extra egg, in other words.
So what we're saying is we're
Yes.
going to take the control, the one that we have just measured now, that was the procedure. And we want to change this into an investigation. So we have to change something. And we ask ourselves the question, if we are so interested in the height of the muffin, what can we change that will either increase or decrease the height of the muffin? And the first question that we ask, which of the ingredients could I add or omit, just leave it
We
out,
can take away as well.
and that would affect the height of the muffins? And we looked at the ingredients so that we can formulate a hypothesis now. So the focus question is important to lead you to formulate the hypothesis, because your hypothesis would be like a calculated guess as an answer to that focus question that you have just asked. But before we get there, let's see what is a hypothesis. Lorraine.
Right. Remember, we have a focus question, and we also had an aim. In other words, to find out, to determine the effect of adding a factor or taking an ingredient away on the height of the muffin. And the question, as well as our aim, needs to, or those two need to help us formulate our hypothesis. Now, if we look at our slide, we can see, number 1, is that the hypothesis is an attempt to explain some event. In other words, it's in a way an answer to that question. The second one is that it's to this event or an observation that we have with the information that we have available. Remember, we haven't done any investigation yet. Colin mentioned earlier that it's a calculated guess. In other words, it's an informed guess. You think that adding an extra egg will increase the height of the muffin. Or you can say, no. An extra egg, it's not going to work. I think it will decrease the height of the muffin. It's a statement.
And since you
Yes.
say that, Lorraine, it's so important, because with the grade 12 learners, we have also seen that so many of them write their hypothesis when they are being asked to do so. They write it as a question.
And even if they write it as a statement, and they put a question mark at the end, it's still a question. We have a question mark to indicate a question.
And even if you start with how or what, and it sounds like a question and there's no question mark at the end, it's still a question.
Yes.
So it should be a statement. And as I said, very easily, if you have your focus question, let's see, for instance, if we have, but let's first see what
We're
a
still busy with the
hypothesis
hypothesis.
consists of. Yes.
Yeah. In other words, this calculated guess, this answer to our question with the information that we have available now, this statement, must contain 2 variables. The independent variable as well as the dependent variable. It must state the relationship between the two. What have they got to do with each other? It must be testable. And when you write it, you state the independent variable first, that's the cause of what we're doing. And then the dependent variable, the effect, will follow. So there you've got your 4 aspects. And you get 2 marks in a test or an exam, which might not sound like a lot. It used to be 3, but it's 1.33% of the of your question paper. So it's 2 variables must both be included. It must be a statement that also gives the relationship between the 2 variables. You have to be able to test it, and you first mention your independent variable and then your dependent variable. So, what about our hypothesis for this investigation?
Let's see what focus question
You must
we can ask.
formulate your hypothesis according to your focus question. Yes.
Right. So now we looked at all the ingredients and we already showed you all the ingredients that we can change. And now we ask the questions. Will an extra egg in this vanilla muffin recipe mix? Will it now? You must listen carefully. I've written down 3 options. That's the relationship. Will it decrease? Will it increase? Or will it have no effect? You can only mention one.
You must decide.
Yeah, you must decide because you are going to make a calculated guess.
Yeah.
So you can use, the question is, will an extra guess, will it have a decrease, an increase, or will it have no effect in the height of the muffin? Now your hypothesis then will be something like an extra egg. You see there, it's an answer.
Yeah.
An extra egg in this standard vanilla muffin recipe will have a decrease in the height of the muffin. That's one person there will say that. Another person will say an extra egg in this muffin recipe will have an increase in the height of the muffin. And another person will say, but an extra egg will have no effect in the height of the muffin after we have baked it.
Sorry, I just made a change. There was a serious mistake. There was a question mark.
Really?
And I took it away.
Oh, sorry.
I had to
that
do
is
that.
the slide of this. I am so sorry for that. I do apologize.
But we made it on purpose so that they could see it shouldn't be there. Joke that, right? But okay, let's go back to our slide.
Right. So let's look at this. So either now you must decide. So you say an extra egg will have a decrease in the height of the muffin. That's it.
Or you can say.
What did we say? We start with our independent variable. And that is the one that you change. And what are we going to change? We're going to change the amount of eggs that we've used in the recipe. So an extra egg, that's your independent variable. And what will it do? The relationship then is it will either decrease it. Let's say it will decrease the height of the muffin after it has been baked. What is the one that we're going to measure? That is our dependent variable. So we're going to measure the height of the muffin. And there we have your independent variable, you have your dependent variable, and you have the relationship between the two that we have stated. And that is simply that. That's your hypothesis. And if you have always struggled with it, we hope that this is as clear as daylight to you. Right. So there we have, we've added the extra egg. And so we see, good, we are going to change. So let's measure and see. What did we say our hypothesis was?
Well,
that an extra egg will decrease the height of the muffin after it has baked.
We've done our control, and now we're going to do the one with the egg and see what happens.
I wonder if one of them, I don't see any questions coming through
they
here.
must ask their questions.
Yes, grade 11, you must get used to it because next year when you're in grade 12, you're going to have a lot of telematics lessons where you have to respond to our questions.
In the meanwhile, I'm measuring.
Oh, and I forget
In
to
centimeters. Right. Oh, there
That's
was
also
a change
important.
here.
That's important. If we look at our slide there, you can see that we have to measure it in a certain unit. Look where the unit is written. The unit is written up in the label, right on top. So what do you see? We have the muffin with all those changes that's going to take place. So your independent variable you have on your left-hand column and your dependent, the one that you measure, will be on the right-hand column.
Measure,
That's
sister.
also, okay, you've written it down. You can also work out.
Mine, the first one was 4,4 and the second muffin was 4,6.
Okay, mine is 5 on the dot, the first one.
Okay.
Cool. And the second one, I'm a bit slower than Lorraine today. I think I'm tired of baking all these muffins.
I hope you haven't eaten.
This is also 5.
Okay.
And that one
Right.
is also 5.
Okay, so in other words, 4,75 between the two of them, 4,7 because that one is slightly less. Yes. So
Now let's go back to our hypothesis.
yes.
So we have something that we can compare to. And if we look at the whiteboard there in front of Lorraine, look at our control. The average of the control was 4,5 for our standard recipe. When we added an extra egg, we can definitely see there was an increase. So
Look
what
at
does
the
that
average.
say about our hypothesis, Lorraine?
Yeah, why do you always get the higher muffins?
I don't know, because
but
you
anyway,
give it to me.
What does it say? Does the information that I have here, that I've written down the average, does it support my hypothesis or not?
That's very important what you say. We don't prove a hypothesis.
And
we
can't
test it,
yeah.
and then we see, with our results, we look whether it is supported or whether it is not supported.
So you can't say, I prove my hypothesis.
No.
You can't say my hypothesis is correct or wrong. It's supported or not supported. And that is important. And you will find that previous textbooks and even handouts talked about the hypothesis being accepted or rejected, or being proved correct or wrong. Remember, now we're telling you, and the teachers out there, that the terminology used is the hypothesis is supported or not supported. And is our hypothesis supported? What do we say? Will the adding of an extra egg, will it decrease? Remember we said it's going to decrease the height of the muffin. Will it decrease the height of the muffin? No, definitely not. Is our hypothesis supported?
No, definitely not, because now we have tested. Tell me, how can we improve the reliability of those results? We've already tried to. How did we do that? Instead of using 1 muffin, we've used 4. We have extras, don't worry, we have 6. But for time, we're only going to measure 4. But we could actually have more.
What we can do is, and I have to say thank you to Colin, who's been baking muffins all these years. She's an expert. But what if she takes a shortcut and she cooks? So I can also go and use the same recipe, same procedures, same apparatus, that is important, and I can go to her home ec or consumer studies class where they baked it. I can use the same oven. Remember, everything must be the same. And I can see if my results correlate with her results. In other words, we can, by having more muffins, we increase our sample size. By me also doing the investigation, and Colin maybe doing it once more, we repeat the investigation, thereby improving the reliability.
Can I say something to
Yes.
them? How are you going to remember this? And the way for you to remember it very, very easily is, when we concentrated on keeping the certain variables the same, can you see what did we increase? The variables. When we kept all the variables, listen to the letter variables, we kept the same, and we increased the validity. So they have a correlation between the sound, the
variables,
okay?
validity.
Here you say, if we repeat this investigation, we can increase the reliability. So you have an easy way of remembering it. So when we keep the variables the same, we increase the validity, and when we increase or repeat this investigation, do it once more or twice more, then we increase the reliability. And you definitely have to know the difference between those two concepts, validity versus reliability. Let's continue, and we have another question. We say, let's do another investigation, totally different
This
one.
was now one investigation.
Yeah.
We've got our results. Now we start all over again with a second investigation. That is important. Sorry, Colin, for interrupting you here. But it's important that our learners know we only test one factor at a time. I can't add another egg and some more water. I first test the effect of the egg, and then I make some more muffins, testing the effect of more water. Right.
Because if we look at the results, and you can see we had different results, we had different sets of muffins. If we should test 2 or more variables, independent variables at a time, you're going to look at your results and you're going to say, now I wonder, which one? Is it the water? Is it the extra egg, or which one actually had an effect on the height? That is why we only use, or we use one independent variable and test it, and that is also increasing the validity of our investigation. Right.
Sorry about that.
Let's get to a new one.
Right.
Now remember now we've scraped it off the top, and we're doing a brand new investigation because we are not satisfied with the height of the muffin. We said, let's take another ingredient and let's see what an extra 100 milliliters of water.
What we're actually trying to do here is we want to set up a muffin shop. And we need to see what we can do to make the muffins bigger so that we can get more money. Okay, we've already had the extra egg. You see, we can also use the taste of the muffin as a measurement, as a dependent variable. But is it really a reliable measure? Because what I like something more salty. Colin might like something more sweet. And if my muffin is too sweet, I might not like it, even though other people might think it's the perfect muffin. So taste is very subjective. We need an objective, measurable factor that we test.
Right, there we have. So the focus question there, so we can have our slide in front of us. We say, will an extra 100 milliliters of water, will it decrease the height of the muffin? Will it increase the height of the muffin? Or if you like, let's say we only want to increase it. Let's make it easier. So will an extra 100 milliliters of water, and then we formulate our hypothesis and we say an extra 100 milliliters of water will increase the height of our muffin because we want a higher and a bigger muffin.
That is our hypothesis.
So it's easy. An extra 100 milliliters of water will increase. That's our answer. That's our calculated guess.
And remember, we still have our original control measurements. So we're going to now look at the increased with 100 milliliter of water, and we're going to compare it with the control.
So let's measure. Let's go and measure. Seems like, okay, 3,2.
You've got 3,2. I've got 3,6.
And here I have 3,6.
Another 3,6. Let me measure here.
Now I can ask the question, why is it that 3 of the 4 muffins have an average of 3,6 and the one is 3,2? Why is the one so much lower?
Would you believe it? This one is 3,4.
Oh. So now something there is definitely wrong. If you can just keep it on that slide or on the whiteboard there. If we look at the 4 muffins, they're the heights of the 4. The first thing that we can say is, let's again listen to what the hypothesis was. It says, will an extra 100 milliliters of water, will it increase, that's the focus question, will it increase the height of a muffin? And we said, an extra 100 milliliters of water will increase the height of a muffin. Oh my word, what do we see? Our results definitely show there that it is not so. Because the average height of a muffin there is about 3,5 centimeters. Do you see that the centimeters is written inside our column in those rows there? No, because the only place that you place your units is right up at the label of those columns and never inside the column. And that's very important to remember too.
Now you can see with the green arrows where we compare the muffins with the increased 100 milliliters of water with our control. We can see that the average, and this is a rounded off average, is much lower, a whole centimeter, and that counts. It's much lower than that of the control. Our hypothesis stated that adding an extra 100 milliliter of water will increase the height of the muffin. So what about our hypothesis then?
Is it supported or is it not supported? Once again, our hypothesis is not supported. So what do we need to do? If you want to, we can increase the reliability and we can go and test it again.
Colin, just something our learners need not be afraid of making or formulating an hypothesis that is eventually not supported. That is the nature of scientific investigation. Many investigations started off with a certain idea, and the results were totally different than expected. In other words, the original hypothesis was not supported. However, when you get a question and you get certain information, match your question, your aim, and your hypothesis to the information given in the question. In other words, if the information, for instance, with our table, if we look at our table, if in an exam this was the information given, then they ask you to formulate an hypothesis from this information. Don't say that adding an extra 100 milliliter will increase the height of the muffin, because you can clearly see from the results it's not the fact. This is now if you are given results in a question. Remember, when you do it on your own as a practical, or when you have to design your own experiment and you start off with no results, then of course your hypothesis can swing either way.
And that's actually very important what you've just said there. So in the exams, you might be given an investigation with the results. And that is so true. For those who didn't listen, once again, if you state a hypothesis, then use your results given to determine what the hypothesis. And if we look at that, if we look at our results again on our whiteboard, then we can definitely see there that if we say, because you have your control. What is the control? Is something that we measure against. That is the procedure that we have followed. So here you can either have a hypothesis saying that an increased 100 milliliters of water will decrease the height of the muffin. I have no idea why this shifted to this. And we can also say, if we have our whiteboard again, we can say that an extra egg, it increased the height of the muffin. You see there? You have taken both of those results and you can formulate a hypothesis. So we are going to measure the last one, since we have a little, so 8 or 9 minutes left.
We also need to do our graph still.
Oh yes. So maybe we should.
I think we've showed them.
Yeah.
Time caught up with us, so we're not going to show them the one with the extra baking powder. But taking our results in account, one of the important things in any scientific investigation is publishing your results. And you publish these results as part of your investigation and your report. But what you also need to do is to represent your results graphically. Now, if we look at the slide, just for interest's sake, you can see within the previous experiment, that was the results that we got.
It was actually the ones today.
Yeah, yes. The ones today. There you can see. And so with the control, what happened with the egg, with the water, and with the extra baking powder. So now we need to do it and represent it graphically. Now, on the slide, Colin, it is so important that they know which type of graph to use if they're not told.
Yes. Now, when are you going to choose? And if we look at our results, we must now decide what type of graph are we going to use. Are we going to use a line graph? Are we going to use a bar graph, a histogram, or a pie chart? Now, if we wanted to observe certain trends, now if we talk about trends, we talk about there was an increase, there's a decrease, and then, or there was no change, it remained constant. That is looking at trends, and that we normally take and we choose a line graph. A bar graph is when we want to compare. So now we have to choose. A histogram looks more or less like a bar graph, but all those columns, those bars are closely, or they are next to one another and touch one another, because we are working with continuous data. That means from ages 0 to 9, 10 to 19, 20 to 29, etc., etc. It's continuous data. But here we have an extra egg, we have extra water, we have added baking powder. Those data has no comparison. They are discontinuous data, and that is why we're not using the histogram, we're going to use the bar graph. So a pie chart we will use when we compare sectors, and we don't have that. So here we have.
Pie chart.
While I was busy talking, she has filled in quite a lot of stuff.
I'm a busy little worker.
And that was now the best handwriting that she could try.
It is my best. Right, so what have I got here? I've got a heading, and I quickly wrote this where I need all the information. I need the added ingredients. Remember, I can now talk about ingredients because I'm going to reflect all the investigations. This is my independent variable, the relationship, the effect, in other words, increase or decrease, and the height of the muffin, my dependent variable. My y-axis.
Can
Yes?
I just, because this is very important, for that one mark, what we say there is your caption or your heading should have your dependent and independent variable for the one mark.
As well as the relationship.
And the relationship, yes.
Then the y-axis is where we put our the y-axis is the dependent variable, our results. And it's the height of the muffin in centimeters. And I've put
The
1,
unit's
2,
also
3, 4,
important,
5,
yes.
6. You must have the unit. And you can start there at 0. On the x-axis...
The one thing, can we just stop there? If we look at the y-axis and the x-axis where the two meet in that corner, Lorraine, I've noticed with my learners at my school that when they choose a scale, then they start with 0 and all of a sudden they jump to 400, then they go 500, 600. Can you get a mark there? The answer is no.
Only if you do it like this.
You have to indicate that there is a break, for instance.
You do it like this. We're going to leave that now, so let's quickly do this and see. Now, I couldn't write the words here for my types of muffins, so I have a key. If you can write the words or it's times or whatever, you don't need a key. For the control, the average was 4,5. So I do with a pencil and I draw, I've got a ruler here, sorry.
I just wanted to say.
Yeah. This I won't get a mark for. I need to work carefully, right?
Because we only have like 3 minutes left, and that is why we...
Yeah, the spaces must be equal width, and the columns must be of an equal width. Now the extra egg was 4,7. So that's more or less there. We need to be much more careful when we do it in a test or an exam. I'm using my minutes here. Then 3,5. Sure, that was much lower with the water. And as you saw from the photograph of the results, the baking powder also was much higher. So let's say our baking powder was an average of 5. So now I'm doing this, because baking powder, like an egg, is a rising agent. And please remember, don't do as I do now. You need to be careful and neat, and everything has to be correct. Same space width, same column width. But there you can see the comparison, and that is why we use a column graph, because we can compare.
And if we look at our slide just for the last few minutes or seconds, we can see that there's also more or less one where we had all the different ingredients, the height of the muffins, and the red ones we say that is what you must include. You must include both variables to get a mark, that one tick. Look at the G there, it's for, or it can be a T, it can be the type of graph that you have selected. If they say it must be a bar graph, and it is a bar graph, you get the little tick for it. You can see over there, there's the graph.
There it is.
There it is. And then what you can see there, correct, if all those bars were plotted correctly, you get 2 marks. 1 for the ingredients, and you name the different ingredients. There you can see on top, it's in control, extra egg, etc. The scale must be correct. The height of your muffin, that is your dependent variable on your y-axis, and the units must be included to get that 1 mark. But it must also, you can't start with 0 and go to 2. that one mark, the full mark you get if your scale is correct, if your label is correct, and if the units are included. 3 things you get for the 1 mark, otherwise you lose out.
And once again, it's 6 marks, and these 6 marks are important, whether it's a graph of a scientific investigation or something else. When you do a graph, be careful. Make sure of the correct type. Make sure that you include everything, because 6 marks is a lot out of 150.
And if you look at the comparison there, that's so beautiful for me. If you look and you put the 4
It's
of
lovely.
different muffins next to each other, and you look at your bars and you look at the heights, you can actually see that is what we've measured. Those were the results that we have obtained. And look there, you have your bar graph, and you have seen this. So this is then everything on hypothesis testing that we have done. We have included, we have shown you how to identify your different variables. We have shown you how to plan before you start the investigation. We have actually shown you how to measure, how to record your data, and we have how to take your data and then put it and convert it into a graph. So we've done quite a bit with them today.
I hope our learners kept up,
Yeah.
and I hope they learned something. If they have the handout, go through it as soon as possible so that you don't forget anything we've done. Until next time, when we will talk about human impact on the environment.
Goodbye from us.
Good afternoon, learners, and a warm welcome to every teacher who is also watching this afternoon. Grade 11s, you are in the last stretch of this year. The end of the long year is in sight, and I'm sure that you are looking forward to your matric year, not so? Well, we are here to assist you on the road to grade 12, but you need to prepare thoroughly for next year. First of all, you must be aware of the work that you'll be tested on in 2017. Things like Newton's laws, electrostatics, electric circuits in the physics in paper 1, for instance. And next time, when we do some little bit of chemistry, I will remind you about what you should know from grade 11 and carry it into grade 12. During today's lesson, this is what I'll be asking you at the end of the session. Number 1, what do you know about redox reactions? So please watch out, listen to the definition, try to understand. Number 2, we'll be asking you what are the concepts that are related to redox reactions. What is the terminology? What are the language issues? And secondly, what is your understanding of those terms and concepts? And lastly, we'll be asking you exactly what are these oxidation numbers. Now let me first greet a few people. I notice that New Orleans School 104 has logged in already. Well, good afternoon to you, and I sure hope that you're going to send some answers for me. I'll put on screen now the contact numbers in the studio, which you know, of course. And then I also noticed that I have 2 other visitors there. Welcome to all of you. Remember, the important thing is to contact us. Talking about contact, here are the details. Number 1, you can use your WhatsApp number and then contact us on this one here, 083 792 1239. That's easier, 083 792 1239. And then your SMS number, if you want to send us a message, it will be 31498. And of course, you can also visit us on the website, ite.sun.ac.za. So that's very important that you contact us, but also, once you've done this and you've got some time to play around with your gadget, be it a tablet or a phone or so forth, you might as well visit the Telematic School project and give us a like on that, www.facebook.com and then the / Telematic School project, and like us on that one. Now, what is the plan for today? What are we going to do? We are busy at the end of the year in grade 11, this term specifically, about types of chemical reactions. Just have a look. That is what you've done last term, or you should have done. Maybe some of you are busy, but basically in grade 10 first, you have done chemical reactions, and one of it was that you had to learn about acid-base reactions. This year, you have to learn, or had learned, the most important terminology around acids and bases. You also have to know what conjugate acid-bases pairs are, and you have to know what is neutralization when you add an acid to a base. There's 6 types that you get. And then, of course, you have to understand a little bit of the titration, that is adding an acid to a base. But in grade 10, which you started last year, you've also done precipitation reactions. Yes, that's right. Sometimes also called ion exchange reactions. And this is one of those that you had to do, where a solid is formed in a solution. And then, of course, one of the third ones you've learned in grade 10 were the gas-reforming or gas-forming reactions, where this reaction is driven by the formation of a gas, which is normally carbon dioxide. So the question is, what are we going to do today? Today we are going to focus on oxidation reduction reactions, where there is a transfer of electrons. Well, I'm sure that some of you have heard about that in grade 10, but in grade 11, you've got to take it a step further and recognize those chemical reactions that are redox reactions. So, what is the first step that you have to know? Obviously, you must give a definition, and from there, from the definition, we're going to try to understand it by using the movement of the transfer of electrons from one species or one atom to another one. Right, so let's have a quick look quickly. What are we talking about? Now, here you see something that's rusted. And the question is, how does the rust form? Well, maybe I can give you an answer to that. Maybe we should have a look and see. Oh, so this is a redox reaction. But what does redox really mean? It means that you have a half reaction called reduction and a half reaction called oxidation, and together they form the complete reaction, which we call the redox reaction. Now, what does that mean? It simply means that in this case, you're taking an iron or some piece of iron and you leave it out in the air, and you sure there's moisture at night time, and then a combination between the iron and the oxygen takes place, so you get the iron oxide or diferrous oxide or di-iron oxide if you want to. Now, what happened here was nothing else that in this case electrons were transferred from one atom, the iron, to another atom, the oxygen, like this. This is what we mean. Transfer of electrons took place. And I see my first visitor ask, what is the term, or what does the term redox mean? Can I just quickly speak to my visitor? Well, you've just seen between the iron and the oxygen and the rusting that's taking place, the electrons were transferred. And then I've got some iron here, iron powder that is, and I also had, and I'm going to put it on here now so people can see inside, or I'll put it in here at least so that we can see more of it. There I've got some iron powder, and I also have in this one, I have copper sulfate. So I leave this one. Most of you know the copper sulfate. Yes, you can see it quite clearly now on the screen. So that is copper sulfate and iron. Now, if I want a redox reaction to take place, I just simply put both of them in a little bit of water and make a solution of, here we go, look at this. I make a solution of copper sulfate and iron. And what do I see at the bottom? If I pick it up and I look at it and you look at me, at the bottom I can see pure copper is being formed. Well, I'm sure that you can't see it from such a distance, but there's copper being formed. So the question is, what happened there? Because this is a real example of redox reactions. Let me explain to you on our whiteboard exactly what happened. Please look here. So I've taken iron, that's right, and I've added it to copper sulfate. Copper and the sulfate. That was my light blue powder. And then what happened was, later on, and I'm going to write my answer below it, so later on, what do I notice? When I put this together, I notice that I get iron sulfate. So I had an exchange reaction. That's right, iron sulfate plus copper. And that is the pure copper that I see there. So what happened here? This is what happened. This copper was 2 plus, and this sulfate was as a charge of 2 negative. So what happened was the iron transferred some of the electrons, in fact 2 electrons, onto the copper, and the copper got neutralized. 2 negatives and 2 pluses gave me a 0 copper. So the copper got loose and the copper settled out. And then the iron, of course, became 2 plus because it lost 2 electrons and then combined with the sulfate. And that's why I have iron 2 plus now, because it lost the 2 electrons, and the sulfate, the polyatomic iron, still is 2 minus. So that is really what happened. There was a transfer of electrons between the iron and the copper. So the one was donating the electrons, and the other one was accepting the electrons. So we had a transfer from iron to copper in this case, and that is what that solution. Well, there are two more experiments you can do at school and in order to see what happens. But let me tell you more about magnesium rather, because that's the one that's in your book. So let's quickly have a look at magnesium. There you have the Bohr diagram of the magnesium. Oh, you know it by now so well. You know it is, what do we call it? It is the atom number 12. That's right. So it has 12 protons because that's how we identify atoms. And we know we have 2 valence electrons and 10 altogether, 2 plus 8 of the inner electrons, the core electrons, you call it from grade 10. So that is what we have. Now we see what happens. Let us now quickly let magnesium, because it's a metal, and metals like to lose electrons. You need to remember that. So now, if we add up, we have 12 protons for magnesium, and it has 12 electrons, so 12 protons in there, and then 12 electrons here outside, and 2 valence ones. We find that the total charge on the magnesium is 0, and therefore we say that magnesium is a neutral atom, or we call it the magnesium atom, meaning that it's neutral. But what will happen, and that is an important aspect that you need to remember, that all neutral species, or shall I call it independent separate species, magnesium standing on its own as an atom, has a charge of 0. That we'll talk later about that in the second half of the program. And now what we have to do next is see what happens if magnesium for that matter, lose 2 of those electrons. What happens if we somehow can get another atom to grab 2 of those electrons, a more electronegative atom which can take away those 2 valence electrons? Let us watch the story further on the screen. So what do we know now? That the magnesium atom is neutral. That's right. And now we find if we lose 2 valence electrons, the yellow ones, and they just go lost somewhere to another atom, we find we only have 10 electrons now, and we start making our algebra. There are the 2 electrons that's lost. Someone else can accept it now, or another atom can accept it now. Then we still have 12 protons, because that's how we recognize it's magnesium. But now we only have, what? 10 electrons. And they are negative 10 and plus 12, give us plus 2. So the charge there on the magnesium ion, it's not an atom anymore. Atoms are neutral, elements are neutral, but we find we now have an ion. So an ion is an atom which has lost electrons, which has a charge now, and the charge is 2 plus or plus 2, because that shows a deficiency or a lack of electrons. And 2 means 2 electrons have gone astray. Now, isn't that a wonderful idea, that how atoms lose electrons? And those 2 electrons must go somewhere else now. So let's quickly just summarize what we've seen here. So we say, we write the magnesium neutral atom. That's just my way of writing it. There is no charge on that one. So what do? We write it as MgO, showing it's neutral, and we're talking about that over there. And then we write it as a half reaction. What happened in this one is that magnesium is going to lose those 2 electrons. So what will magnesium look like? Mg2 plus. That's right. So we write it as, those are the 2 free electrons. That means if it's on the right hand side, that those are lost electrons, donated electrons. It means it's free from the magnesium. Just like there's magnesium that side, and here is the ion without the electrons. The electrons are written separately. So we write this one as, watch carefully, magnesium 2 plus. That means this is a magnesium ion, and this I call a half reaction, because this only happens to magnesium. Something must still happen to those 2 electrons, and then we'll get the other half reaction. So we have magnesium neutral atom becomes magnesium ion plus 2 electrons. Isn't that a nice way of writing it? We can actually make an entire English sentence by using chemical symbols. Are you clever or are you not? Let's look at it again, how we write that. Let's quickly look at my whiteboard. So I say I can use magnesium, the neutral atom. That's the atom. And now I'm going to make an ion. And I know that this is in group 2. And therefore it's going to lose metals. They like to lose 2 electrons in group 2. Group 1, by the way, likes to lose 1 electron, all the metals. And I write a 2 plus. But I can't just write that because that is incomplete. Something is missing. And therefore I have to add that I have also lost 2 electrons. Why is that? Because the 2 negatives and the 2 pluses there, those two combined, that must supposed to balance with the other side for me. To get that, so we have to write down negative and positive, and that was the original reactant that we had. Now, let us see who will accept those 2 electrons. Because it's senseless. There's one half reaction waiting saying, listen, I want to give you money, but then there's the money lying and no one is taking it. No, someone must accept the electrons. Another atom, and we call this combination half reaction giving, half reaction taking, accepting the electrons. We call that an electron transfer, and we call this whole, the 2 halves, we call the whole reaction the redox reaction. Let us look quickly about what is going to happen next. Please remember that this is called the oxidation half reaction because magnesium is losing the electrons. Right, and I see someone already before I go on has asked me a question. And the question on the screen is, I think it's Siglova Matebe, a learner from Etembeni Secondary School, said, I want to ask what is the element that is oxidized called? The one that is oxidized is called a reducing agent. There we go. It's called reducing. I like clever questions because I know those learners really want to learn. And I wonder what the rest of you are doing. I haven't seen any questions or answers yet, and you need to answer. Let's quickly look at my screen again and see where we're going. So we call this kind of writing magnesium becomes magnesium ion plus 2 electrons. We call that the half reaction, and because it's losing electrons, we call that the oxidation half reaction. Okay, now we have the screen again. We said we'll be looking at what happens between magnesium, who is donating, and another atom or ion or polyatomic ion that will accept it. So let's have a clear look and understand this concept. The first concept was magnesium loses electrons, had 12, has 10, lost 2 electrons. Someone else must accept it. And here comes chlorine, and chlorine says, I am more electronegative. I am interested in electrons. I want to take your electrons from you. I am an electron thief. I am more electronegative. And here is the chlorine atom. And let's count the electrons. 2 plus 8 gives me 10, plus 2, 4, 6, 7. Oh, chlorine is in group 17, and they are normally very electronegative, and chlorine just needs 1 electron there to fill up there. But there are 2 electrons available, so that means I will need 2 of those chlorine atoms. So let's take the story. So 2 of them come and tell magnesium, listen, each of us need 1. We are hungry for electrons. So the 1 chlorine atom takes 1 electron, the other chlorine atom takes another electron, and then when it gets more electrons than what it usually has, we then call that an ion. So anything with a deficit of electrons, too little electrons, is called an ion. Anything with too many electrons is also called an ion. So this is the magnesium ion, and this is the chloride ion. We know that nonmetals normally get an IED afterwards. Chloride ion and chloride ion, each one has now 8 that side, 8 that side, and this outer level, energy level is filled with electrons, and that one is filled with electrons. So each one is happy, and now they combine because the positives will attract one negative and one negative. All right, let's talk about that again. So what did we see? We noticed the following, if I can quickly get you here. We noticed that magnesium had 2 electrons to give, 2 valence electrons. So magnesium puts its electron out there, and we find that magnesium now becomes Mg2 plus. That 2 plus means there was a loss of electrons. And what happens now? Chlorine comes along, and chlorine says, I am hungry for electrons. I am more electronegative. But we can't have just one chlorine. We have 2 chlorines because each one only needs 1 electron. And so what do we get now? The aftermath of that, we find there's magnesium with these 2, and chlorine says, okay, I will take this 1 electron, so I become a chloride ion, and this one says, no, I'll be able to take another electron from you, and then we see 2 went missing, and those 2 are here now. So that's how we write it. So now we say that the magnesium 1, the magnesium, correct, became magnesium 2 plus. This is called the oxidation half reaction, the loss of electrons. And what did chlorine do? Chlorine said, no problem, no problem. I am simply going to take, 2 of us is coming to take your money or take your electrons, and then we will be 2 chloride ions. That's right, 2 of them. But what do they get from the magnesium? They take those 2 electrons. They take those 2 electrons, and we add the 2 electrons to chlorine. So chlorine says, the magnesium says, I will give 2 electrons. Chlorine says, thank you very much, I will take those very 2 same electrons. And then I become chloride ions. Now, isn't that a nice story that we have here today about these exchanging transfer electrons? So, by the way, what are we discussing then if there's transfer of electrons? We are discussing redox reactions. And just before we look into an exercise, let me just remind you about the following here. The following is true, that we have an oxidation half reaction, loss of electrons, and we have a reduction half reaction. So we have a reduction half reaction, and we have from there an oxidation half reaction, and that is why we call these redox reactions. That is why we call these redox reactions. There we have it. Right, let's summarize the story on my screen. So let's go there now. So what do we have? We have the magnesium, who is then oxidized and lose electrons. He's lost 2 electrons, in fact. And then what happens after that? We find that the magnesium atom, put out all the facts, has lost 2 electrons to form the magnesium ion. The magnesium ion has been oxidized, and the magnesium, which is on the left-hand side, this magnesium, is the reducing agent. So the substance that is oxidized is called the reducing agent. I think that is the question that Sidlova Matebe has been asking me. There's your answer. So how do we write this again? Let me double check and make sure you understand it. Let's look on the screen. And then what do we see? We see oxidation is the loss of electrons. That's right. So magnesium is oxidized. So oxidation is the loss of electrons, and magnesium is called the reducing agent because he's going to give electrons to someone else. That is what's happening. Now, next step. We now watch very carefully and see what has happened here. We noticed that we have the magnesium losing 2 electrons, and we notice that chlorine is ready to accept those electrons. Let me just remind you about one thing before we look again at what we've just seen. Look at here quickly. At the top, notice this is our half reaction, and that is how we write it. We write that the magnesium becomes magnesium ion plus 2 electrons. This is called the oxidation half reaction. That is correct. It's a half reaction because we're only talking about this half. We must still talk about the other half. Everybody ready? Okay. So, no questions, no answers yet. New Orleans, are you still there? Please send in some answers. Can I ask a question so long? What is the function of a reducing agent? Oh, sorry. What happens to a reducing agent during a redox reaction? I would like you to send in, especially for New Orleans, to send me an answer. Next substance that we have on the screen, a reducing agent, is a substance that is oxidized. But now we're going to take the story one step further. We're going to say that chlorine gas is reduced because they gain the electrons. So how do we write that? Or what can we say first about the chlorine gas? Right? We can say that chlorine has been reduced because it gained electrons. Secondly, we can say the following three things about chlorine. We can say the chlorine molecule, Cl2, has been reduced. That means when I use that term reduced, I'm saying gain electrons. The chlorine molecule has gained 2 electrons, and what does it form? It forms 1, 2 chloride ions. That's right. And now, what do I find now? It says here, the last one, the chlorine gas, which is always on the left-hand side. We always talk about agents. Either this is the reducing agent and this is the oxidizing agent, because it's causing the magnesium to receive or lose electrons. So what's the definition of an oxidizing agent? What is chlorine doing? Chlorine, of course, is undergoing what? A reduction. And how do we write this? You see, and I just put it on the screen, that Cl2, those two, they gain those 2 electrons and they become 2Cl minus. Now, how do I remember that then? That when the electrons are on the right-hand side after my arrow, that means the electrons are lost, and that is oxidation. The electrons get picked up while it is still lying there before it goes into reaction on the left-hand side, then it means it is reduction. That's right. That's what we have today. I have a question from Jack Wele, a student from Burgersdorp High School. What is the oxidation number of the element magnesium fluoride? Now, I don't know which element is referring to, but maybe we must just quickly explain to Jack Wele. Just look at here quickly. He's asking what is the oxidation number of magnesium fluoride. Now, if we split this up, we know this is group 2, and we know that this is group 17. Sorry, I'm going to use this number now. Okay, so that means that, and I have 2:1, and you normally know from grade 9 already, that means magnesium must have lost 2 electrons. Take the 2 there, and I take the 1 over. That means I have 1 each here, and they are minus minus. So this one's oxidation number is 2 in this case, and this one is minus 1 minus invisible 1 there. That's what the answer should be. I think that was what was after. Thank you very much, Jack, for that question. So what have we got so far about chlorine? Simply this, that chlorine is reduced, and look how we recognize reduction. The electrons is picked up before you get to the reaction, and then we find that in that instance we have 2 ions, chloride ions, the negative, the charge showing that it has gained electrons. And chlorine is therefore an oxidizing agent, meaning that it is a substance that is reduced. Now, what kind of study hints can one give you? Many of you must have picked it up already, that one of the study hints that we normally give you is the following. Just watch carefully. We say that, you remember, oxidation is loss of electrons, and reduction is the gain of electrons. And secondly, we sometimes see these half reaction tables where they done most of the reductions for us. Look here, there's magnesium, for instance. I could have read it easily. Magnesium It's reduction table, please. So next year or later in there, you learn how to write this as an oxidation. And I go to the next table, I see there's the chlorine gas picking up the 2 electrons to become. So these things have been worked out for us many, many times before. Now it's time for action. You now have to identify some redox reactions. You know what you must look for? Something must lose electrons, something must gain. Here's the normal rule. We say that we have metals normally lose electrons. Group 1 metals all lose 1 electron. And group 2 metals normally lose 2. And aluminium and some others lose 3 electrons and so forth. So, are you ready to look at the exercise that you must do? Let's go to my screen quickly. Now, this activity is on page 2 of your work. You need to start and do it very quickly. I am going to do the first one for you so that we can all see together what you need to do. And then we're just going to do 2 of these, not all of them. Can I quickly get your attention? So what we're going to do, we are going to try and recognize redox reactions, and then you need to say which one is a redox one or not. Let's look at my whiteboard and then we can discuss it from here. Okay, so here I have the same exercise for you. I take the first one and I see that I have 2 potassium, and that's a metal, and I bromine from group 17, bromine gas, and this one is more electronegative, so this one would like to get electrons. So it would like to steal electrons. This one, however, is the one that is a metal, and metals normally have delocalized electrons, and they are going to lose electrons. And so if we look at that, we see that this has no charge, is neutral, and that one is also neutral. And then what do we notice? We notice that potassium likes to give off, group 1 likes to give off 1 electron to this one, this 1 electron. But now I have 2, so 2 electrons come over to Br2. That's right. So when I look here and I see that this is an ionic compound here, metal plus non-metal, I notice that the K ionic must be K plus and the bromine must be negative. That's right. That means, let me look again, that means if I now compare before and after, I notice neutral, all electrons, all protons there, and this one is K plus, which means this has lost electrons to bromine. So therefore, the loss of electrons, let's look again, loss of electrons, oil, loss of electrons, oxidation is loss of electrons. That means the potassium has undergone oxidation. So I can say potassium has undergone oxidation. That's right. Let's look at bromine quickly. Let's see what's happened to bromine. Bromine was nicely sitting there with its, it was a molecule, a Br2 molecule. That means Br bonded together, and it was neutral. And later when we look at bromine, we see no, bromine is negative. So it appears that bromine, which has now got the negative charges, and those negative charges can only indicate one thing, and that's electrons. That means bromine afterwards actually got electrons, and therefore it underwent reduction, because remember, reduction is gain of electrons. Reduction is gain of electrons. Is that clear? So therefore we know that this is a redox reaction. Let me take another one for you. Let me take the last one, for instance, then you can do the 2 yourself. If I look at copper and I see that copper 0 is standing on its own, so it has no charge. And if I look at copper later again, I see that copper has a 2 plus. So how can a neutral one become plus? Oh, only when it loses electrons, and therefore It is oxidation, because oxidation is loss of electrons. You get that? So therefore I can safely say that this one, although I didn't recognize both oxidation and reduction, I can see, okay, in this case it is quite clear that the oxidation happened there, so one of the others must have accepted the electrons and the reduction would have taken place. I hope I've given you a good idea now of how to tackle such a question. But the next one that you have to tackle as well, before I answer Sidlova Matebe's question again, I have another one for you. While you quickly work on this one, I'll look at the question and then I'll speak to you in a minute about it. I'm giving you exactly 2 minutes to try and answer this question here with the help of your teachers being around. Quickly answer this one for yourself. Okay, I think our 2 minutes are through. Let's see how far you got with those questions, everybody. What was the first question? That you had to write down a balanced chemical equation for the oxidation of reaction. Now, let us quickly just look down here and see what I've written down here. I've written down the full equation. This is the full, hopefully, redox reaction. And now they ask me to write down a balanced chemical equation for the oxidation of reaction. That means I must only take one of these two and write out an equation with an arrow. And how do I know oxidation? Normally metals, they have delocalized electrons, they would lose it. So I can safely write Na, that is right, which is normally neutral. You will lose the electron and become Na plus. That's easy, lose one electron because it is in group 1. That's right, it is in group 1, and metals in group 1 normally lose 1 electrons. They have delocalized. And chlorine, on the other hand, chlorine is more electronegative, so chlorine would like to take it. But now I must show the extra electron that it loses. So I must show who loses electrons and who gains the electrons. Sorry, my apologies. I must not put that in there. That must be 1. Let's write it as 1 electron then. So it's lost 1 electron. Okay. And now for the second step, I now need to write, and this would be loss of electrons on this side. Loss of electrons is called what? Oxidation of reaction. Is that clear? And now I go to chlorine. So I'm going to write the chlorine, which is a gas, and therefore chlorine is more electronegative. Chlorine is group number 17 and it would like some electrons. It needs 1 electron each. It has how many valence electrons? 7. So it's in group 17. So it means it will need 1 electron each. So therefore I can safely write that chlorine, each chlorine will get 1 electron. But because I have 2, I need to write that 2 of them. But I need to indicate that this one is gaining the electrons. Which electron? That 1 electron there. So it gets 1 from sodium and another sodium. So it gets 2 electrons, eventually 2 electrons. So these two will get the 2 electrons. So I write plus 2 electrons. But that is not totally balanced. 2 electrons, 2 sodiums. I have to start off with 2 sodiums. So which means if I go to the top now, I have 2 of these sodiums. and that, and then I put a 2 in front there, then I have 2 on that side. So I have 2 there now, I have 2 there, I have 2 there, and I have 2 there as well on that side. Okay, so those are the two half reactions. So what do I call this half reaction here? What do I call this half reaction here? I call that the oxidation half reaction. And what do I call the half reaction here? I call that the reduction half reaction. Okay, now I see one of the other questions that they have for you is, write down the name of that is the reducing agent. So reducing agent, let me quickly think, reducing agent, cause something else to be reduced, itself is oxidized. So which one is oxidized? Look at here quickly. So it means that the sodium is the reducing agent, because, sorry, the sodium will lose electrons, so sodium undergoes oxidation, so sodium is reducing agent. That's right. Now, let us therefore look which one is the oxidizing agent. That means the one that is reduced. So this one is reduced by gaining the electrons, and therefore this is the oxidizing agent. So that's how we have to answer that question. And thereafter you can do as many exercises you want to. We've given you enough. You can do it with the help of your teachers. Now, what is the next question? I have seen two questions here. Siglo was asking, if the number of a species becomes positive, will the species become oxidized? So I think the name is Siglova. I would rather say if a number becomes more positive, then it becomes oxidized. Why do I say that? Let me give an example of why I say it. Quickly, if I then say magnesium is now 0, and then it becomes more positive, then it is oxidized, because I can get copper 1, for instance, and then it can become copper 2 plus, but then it is also oxidized because it has become more positive. Sidlova, Matebe, hey, my friend, I must honestly say that I think you are starting to understand that we are corn, because it means that you have an idea about the oxidation. Then I see as another question that Sitlova again is saying, but this boy is hard working today. Eh? He says oxidizing agent is an element that is reduced. Now I'm asking you, do we have a clever scientist on that side, or do we have a clever scientist? Please tell your teachers that you want to become better and they need to give you necessary assistance. Right, everybody? So that takes care of what we mean by oxidation, reduction, what we mean by reducing agents, oxidizing agents, etc., etc. Now we come to part 2, which I'll just quickly summarize for you. What are oxidation numbers? On my screen, please have a look. We are asking you that you must tell us what oxidation numbers are. And you're going to ask us, but I know that already. I've learned that in grade 10 or anyone else or anywhere else. And here is our official definition. We say that the charge, an oxidation number, is the charge an atom would have if all its compounds were ionic. Now that is a strange thing to say. Let me quickly just talk to you about it. If they were ionic, that means if I have an example, I have something like this, HCl. This is not a metal and a nonmetal. These are two nonmetals, so this is a molecule. But if we give oxidation numbers, we ask ourselves, how many electrons would hydrogen lose? And the answer would be hydrogen would lose 1 electron and become H+. So now we say that although in this compound they have no charges, they share electrons in molecules, we say we give it a charge now, and we say as if it would be an ionic compound. And the other one would gain the electrons, and we would call that a negative charge on that one. So we would say they do not have charges, but that would be the charges they would have if they were ionic compounds. That is what we mean. And then two things you have to remember about these oxidation numbers. But by the way, I say that this one here has an oxidation of 1 plus 1, and that one is an oxidation number of minus 1. That is what we call it. And now watch carefully my next step. One is that I have on my screen now for you, I am saying that if an oxidation number increases, then we have oxidation. But if the oxidation number decreases, then we have a reduction. What exactly do I mean by that? What exactly do I mean by that? Let me give an example quick before we look at the rules for oxidation numbers, and that's where we're going to leave it in today. Let's look quickly. Let's look again at sodium, one we had, and chlorine, right? And we notice that it becomes sodium chloride. Nice. And now we say this one has no number, this one is a neutral atom, but here it is plus 1 in combination. So it went from 0 to 1. Is that up or down? That oxidation number, oxidation went from 0 to 1, so it went up. And therefore we call this process oxidation. Everybody is happy about that. So that is oxidation if the number goes up. Let's watch this one quickly here. And we see that this one here, on this side, neutral chlorine, although it should be chlorine 2, of course. And then we find that is 0. And here it is minus 1 for each one of them. So what has happened to this number? This number went from 0 to minus 1. That means the number went down. So when the number goes down or decreases, then we are saying that this is a reduction. That is a reduction. That is what it is. So let's look at my screen again here. And let's see if there's no more questions. One more. That is against its law, and it says the oxidizing agent is an element that is reduced. It seems like we have one person in this universe here. We have only one person and talking all day and giving the answers. I'm very happy, but what is the rest of you doing? What are you doing? What are you busy with? Are you focusing? Good. Let's look at my screen on the side. The oxidation numbers is a number that atoms would have if they were ionic bonds, and if the oxidation number increases, we call that process oxidation, and if it decreases, then we call it reduction. Now, for some rules before we actually end off this afternoon. One of the rules is that you need to know and identify the oxidation numbers of some substances, and here are the rules. Just look at my screen. 1. I call it the 1, 2, 3 rules, or 0, 1, 2, 3 rules. One of it is the following. We say that all three elements has an oxidation number of 0. So zinc and oxygen and hydrogen, they're all there. And now the ones with the ones, we say hydrogen normally is plus 1, except if hydrogen is a hydride, which means it stands at the end and not first. Then it is minus 1. So here sodium is plus 1 and hydrogen is minus 1. But normally hydrogen atom is plus 1. Now let's go to the, and all group 1 atoms also has plus 1. Now we go to the plus 2. Let's see. Oxygen atom is normally minus 2. That's right. Oxygen atom is normally minus 2, except in peroxides, then oxygen is minus 1. So 0, all three elements. Hydrogen atoms is normally plus 1. Oxygen atoms is normally minus 2. And now we come with more dangerous rules. We say if I have Br minus, then it means the bromide ion is minus 1. And if I have sodium plus, it means the oxidation number is plus 1. So that charge there tells me what the oxidation number is. And sometimes we have many atoms together, ions. We have polyatomic ions. One sulfur, 4 oxygens is polyatomic, and its charge is 2 minus. So now I want to work out, and this will be my second last point. I want to work out what is sulfur here. Let's quickly look on my screen and see how we work out. So I have the sulfate ion, which all of you should know from grade 10. And I want to know, according to my rule, that means that is equal to minus 2, because we say this whole thing is equal to minus 2. That is interesting. But now I can say, well, I know the rule for oxygen. Oxygen is normally minus 2, but I have 4 of those. So I have 4 of those, and that is equal to minus 2, plus I have sulfur. Does that make sense? So I have sulfur, and I want to find out the oxidation number of sulfur. So I have sulfur, plus I have 4 oxygens, and 4 oxygens, the rule which I just said, was minus 2. And therefore that's equal, and I can solve for sulfur. I say sulfur minus 8, because that is what 4 times 2 is equal to minus 2, and therefore sulfur is minus 2. I take the 8 across, plus 8, and sulfur is therefore plus 6. So there's the oxidation number of sulfur. Isn't that a nice way of working this out? So, what did I say? I said to you 2 things. Let's look at it again. That any polyatomic ion like the sulfate ion is equal to its ionic charge. This is what I mean. Have a look again. Have a look again. Any polyatomic ion, poly means many, many atoms, is equal to its charge. So that thing is equal to that charge there. And then I can work out. I always go for the one that I know first, and then I find the unknown one. Okay, so let us quickly look at the last point, and then we're going to summarize for you. We're saying that atoms in covalent compounds, some of them can have different oxidation numbers. Look, for instance, here sulfur. Sulfur here, for instance, is plus 6. I just worked it out for you. Sometimes sulfur can be plus 4, and sometimes sulfur can be plus 2. Now, that is really some rules that you have to go learn. You've got in your booklet a number. Please learn them. You're going to need them in grade 12 next year. Now, just 2 messages quickly that I want to get to you. And that is important that we get those messages. And the message is, my name is Kamogelo Mahadika from Bishop Demont Secondary School. What are other physical examples of the oxidation process? Well, we get lots of them. We get electrolysis, for instance, where we coat things, galvanize things, for instance, and we separate salts, where we make new materials like copper, for instance, and we can make sodium metal, and we can make aluminium. Those are all physical examples. And I'm very thankful, Kamogelo, for that question, because it just shows how interested you are. Right, let's go for a summary today. Do you still remember that I've told you, 1, that redox reactions is called the transfer of electrons. And oxidation, the oxidation process is the loss of electrons, and the reduction process is the gain of electrons. We told you that you must also know oxidation numbers. When an atom is standing free on its own, or in a compound on its own, then the oxidation number is 0. That hydrogen is normally 1, and oxygen is normally minus 2. We also said to you, if you have a charge on ions, then the whole compound or polyatomic ion is equal to the charge, and you can't lose charges along the way, and covalent molecules must be treated like they are ionic substances. We also informed you that if a number increases, like sodium from 0 to plus 1, then we call that process oxidation. If a number like, for instance, bromine decreases from 0 to -1, we call that process reduction. And lastly, we said to you that you must remember how to write half reactions. If the electrons are lost, it's on the right-hand side. So this one undergoes oxidation by losing electrons, and this one then is the reducing agent. If we gain electrons, we write the electrons on the left-hand side, and here we add up the entire reaction. One last thing, that means we are ending off now, and all I can tell you is on the screen that we're meeting on the 25th of October again at 4 o'clock, and then we'll be discussing gold as a mineral which we have to process and mine first and then process. Goodbye, everybody. See you next time.